Jordan is there. Jordan said that he will not have his audio and video on. Apparently, he rents a house, or his renter's basement is flooded and he's working on it. So probably if he puts it on, it will
probably through his phone.
Yeah, he said he'll be attending using his cell phone. So that's what he said.
I've been at meetings like that before.
Have you?
And I've listened, like if on a Friday, if I really wanted to get back home, that I would.
Oh,
listen
our seminars.
to the seminars.
Some of the advantages of having this online.
Well, the nice thing is in my car, it automatically feeds through and it's coming through the speakers.
Nice. It's like having a speaker in your back seat.
Hands-free.
Yeah. Oh, what's this? Hey. Let's see. Zoom out.
Done.
This earlier out there.
Yeah.
Luke, but I need to set up my. Hello, Luke.
Hello.
I just finished the homework for the quorum.
Yeah.
18 pages.
18.
I did matrices and I did a lot of work.
Yeah,
Showed a lot of steps.
yeah,
So
that's good.
My homework is so much
yes,
better.
E&M is easy. He's gonna have to step. He said he's gonna step it up, make his work harder.
Oh, no.
No, me? No, I didn't say that. I'm glad that.
I just wanted to see if anybody can.
I often feel guilty that it's overwhelming the students, especially in the first few weeks. It takes some time to get used to the amount of pages you're filling in.
I'm very compact and I use both sides. So if I was able to do this assignment on just one page,
I was only
well, two
Three
pages, yeah, so that's comparable.
Yeah, I should pick those homeworks and say this is the standard. Like there used to be Dustin, right? He's a grad student here, right? He doesn't like filling in more than a page. So he will like to fill all my homework in one page.
Wow.
So he'll squeeze it in here and there or jump steps and all. So I think it was his policy or something.
Okay.
I mean, he didn't say it like that, but at least I observed that it was always squeezed into
Yeah,
one.
I prefer to keep my font consistent and, the lines be clear.
See some obsession right now. Homework problem. Homework cannot go beyond one page. So typically, when I was a grad student, I used to fill pages. I used to like filling pages.
Good feeling.
I had a friend in grad school who was thrilled they got rid of the form feed printer. And so he ended up with like a stack of printer paper about that tall.
So continuously you can go.
So he could hand stuff in and not wait for your own paper and have scratch paper to his parts content.
Okay. All of us here. 1, 2, 4, 6, I guess. Yeah. So I'll zoom it in, so I think this part I can stay. Three weeks from today, we have. Any comments in general? How's the homework? Is it reasonable?
It wasn't horrible. It was, there was a couple of tricks, I think, that we just had to consider, but
Yeah.
it wasn't lengthy.
Okay, good. Yeah, that's good. Yeah. Yeah, tricks. Yeah, that's hopefully that's helps in the next steps. Okay.
In fact, I thought maybe it's like, am I doing this right? Because I didn't take as much space as I normally do.
As you're used to, huh? Yeah.
There's also only 40 points compared to the first assignment, which is 90 points.
I think.
3 problems and 90 points. This is 2 problems, 40 points. So it's smaller assignment.
Points I just randomly put.
Yeah.
Yeah, I think, and they're like each homework is equally weighted. Like it's not that if you have.
Well, no, I know.
Yeah.
That's,
So,
okay, well.
right. That's probably not obvious during. Like
Gotcha.
eventually it doesn't follow.
Yeah, no,
Suppose there is a
that makes
homework
sense.
which is 500 points,
It
and
doesn't
there's
matter,
another
yeah.
homework which is 30 points. They're equally weighted.
Yeah, gotcha.
So, which I never stated in front.
No, that makes sense, yeah.
And I do have that option that I can do the other way, but choose it this way. Okay, so we started on circular wire, and we try to calculate the magnetic field and the vector potential at the center of the wire, and we got an answer for the magnetic field, of course, and for the vector potential we got an answer, but then we said, oh, it's not very useful because you cannot calculate the magnetic field from that point. So let's do a similar thing for on the axis of a circular loop, and then we will do some tricks, or I shouldn't say tricks, an approximation that will actually let us get the field due to a circular wire exactly in an approximation. That is to say that the radius of the wire is very small. Make it, or the observation point is really far away relative to the radius of the wire. In that case, we have a nice simple expression, and we'll come back and get the complete expression later on. Okay, so zoom in it. Yeah, we did zoom in. So this is a circular wire, current carrying wire, uniform current in it, and for now, let's say we are on the axis, like the observation point is on the axis. So that's your loop, and that's a current I going through that, and we need a radius for this. So let's say that's radius is A. Hopefully visible. And let's want to emphasize some of the doable things on this, and let's say the observation point is on the axis of the ring. So in general, you have an observation point R here, right? That's where you would like to calculate the observation point. But before that, let me first write the current density, right? So current density for this loop, you try to say prime, right? And it just comes to sources, it is equal to I times, and or current per unit area. So area is this wire, the cross section of that wire. It is of rho minus A, the radius, and then if you think of it as having slight thickness, the wire, then the Z also comes in, so it's delta of Z. And let me say it is in the XY plane, so that Z is exactly equals to 0. We motivated that last time. and the vector potential is given in terms of the current density as not over 4 pi cube or prime. Or minus 4 prime. And R could be anywhere here. Last time what we did was we put R at the center of the circular loop. In that case, this goes away. It's just R prime, which is magnitude of R prime is just the radius A, and we calculated that. But now let R be on the axis. So that means it could be somewhere here, but not necessarily on the center of the center, not necessarily on the center of the wire, anywhere on the axis. Right? That means that you would say, let's say that AR is actually equal to Z times K hat, if you want. It's X and Y is 0. Okay, so that means this is A0, 0, Z. That's what we mean. That sense. So it's equal to mu naught over 4 pi d cube r prime. So again, let me split this. I have 0 to infinity rho d rho prime minus infinity to plus infinity dz prime and d phi 0 to 2 pi d phi prime. Oh, what is wrong in the current density?
The coordinates are prime.
Yeah, that's one thing, sure. That's, I didn't even notice that. Okay, more, yeah, that's important. And there is one more. Like something is missing. Like left-hand side is a
unit vector.
Yeah, very good. Unit vector, right? Yeah, good. So left-hand side is a vector. Right-hand side should also be a vector. So add to the direction of the current, which is circular. So it is phi prime. It is phi prime. Now phi prime hat, remember, is coordinate dependent. So that cannot be replaced with phi hat. When it comes to z prime hat, you can replace it with z because they are the same. But phi prime hat at the observation point and source point need not be the same. So we have to be careful about that. So I times so phi prime hat, and then that is I, and then of rho prime minus a z prime minus 0 divided by r minus r prime. Right. In general, r minus r prime is we are in cylindrical coordinate, notice. So this will be z minus z prime square. So this is the most general. I'm not yet putting z rho and z prime equal to 0. So this is equal to, in general, plus rho square plus rho prime square. This is the radius of source, radius of observation point, and plus 2 times rho prime cosine of phi minus phi prime. Okay. Show that this magnitude is indeed equal to this. So that's your quiz. How about that? So show this as a quiz. Evaluate the magnitude to be exactly this. Take 2 points, write it in cylindrical coordinates, subtract, and get that. Good. But we have a simplification here, significant simplification, because this is x equal to 0, y is equal to 0. We're on the axis. But if we are on the axis in cylindrical coordinates, rho is equal to 0. The observation point rho is equal to 0 in this case. So if observation point rho is equal to 0, the denominator, this goes away. Right? That's because we are on the axis. And the whole of the cosine term also goes away. That's because we are on the axis. That's a simplification you get if you're on the axis. And that is because we are on the axis. From that point on, I can still do the integral rho prime and z prime. That replaces rho primes and z primes there. So that's equal to, now I do the integral, mu naught I over 4 pi. And that is a rho prime gets replaced with a. I have 0 to 2 pi d phi prime. So the direction remains phi prime. And the denominator is z prime has to be set to 0. So that's z squared plus rho prime is a. But z does not depend on the primed angle. A does not depend on the primed angle, right? Because a is the property of the loop itself, and z is this point here, this distance here. Where which part of the loop does not depend on the z, right? So z depends. So that whole denominator comes out. Oh, am I in the? Yes, I'm in the board space store. So this means I can write mu naught over 4 pi and I times a over c squared plus a squared. And you have 0 to 2 pi d phi prime phi prime. Okay. And what is that integral equal to? We came across this last time also. Integral of a unit vector that's tangent to this loop, but integrated over all the angles. What's that integral equal to?
Zero.
So think of this as a, so that's the current carrying loop. Right? Phi prime is always tangent to this. So that's your phi prime. That's your phi prime hat. And as you change the angles, this will always be tangent and it's of the same unit length. But if I integrate them all together, add them all together, when I integrate it, adding these are vector additions, right? Or add up, and how much is that?
0.
Right, it has to be 0, right? Because they will all add up. You can see it more explicitly if you want. That's a geometrical proof, should be very convincing. Doesn't need anything more, but if you really want a more explicit answer, phi prime as a vector, remember a rho prime hat, let's say, is equal to cosine phi prime I hat plus sine phi prime j hat. Okay, so that's an explicit expression in terms of rho. So this is I within that space. Yeah. So this is rho. Okay, I'm talking in primes. Even rho will pretty much go through, and that's your angle. That's a unit vector. So it's cosine phi sine phi using the right triangle. If you want, the x component is cosine phi, y component is y prime. Phi prime hat will be perpendicular to this. Notice tangent is always perpendicular to the radial vector, so it is somewhere here. If you move that down there, that's your phi prime hat. If this is angle phi, that's 90 minus phi, that's phi prime. So the second quadrant, so the x component will be negative and y component will be positive. But then x component is now using the right triangle property, it will be again sine phi prime. Again, because it's unit vectors, right? No coefficient. So you have the structure that, in fact, derivative of rho prime hat is actually phi prime hat. The sine phi derivative is sine phi. In fact, take the, what's the derivative of rho prime hat with respect to phi prime? So there's this property that you use that in classical mechanics a lot, right? Or mechanics.
Rho prime hat.
And a small correction. Centripetal acceleration, like velocity. Acceleration is something here. So I'm saying this is what you're suggesting, right? I'm saying there's slightly something missing here.
The minus sign.
Minus sign, there you go.
I said a minus.
Oh, you did I didn't hear. Sorry.
That's okay.
Okay, sorry. Yeah, I didn't hear it. Good. So that's, how would you say this? This is velocity. This is for circular motion when it is constant. This is velocity as a position, change in position with angle. So this is velocity, change in velocity with angle is the centripetal acceleration. So that's
So that's really just the radial and transverse components that I was talking about earlier.
Oh, there you go. Yeah, but probably the simpler in the sense that it's uniform, right? If it is not a circular motion, if it's an arbitrary, then there is a second term, right? Coriolis. Yeah, but there you go. Yeah, good. Okay, so because of that, but I said I wanted to show you this more explicitly, right? So then you would say this is mu naught over 4 pi. Like if the geometry is not convincing enough, it should be. I mean, geometry captures most of it. And this is cosine, sine phi, minus sine phi prime I plus cosine phi prime j. Now I hat and j hat are not coordinate independent. You can bring it out. Now there is an integral over sine phi, but it's going from the complete period 0 to 2 pi of a trigonometric function is 0. So integral of each one of this integral is 0. So that's equal to 0. No doubt. That's okay. So it's not very useful exercise in a sense. You got the vector potential, good. But if you want to calculate the magnetic field out of it, You cannot because it is 0, right? You would think, so what is magnetic field on the axis? It will be del cross A. But whenever you want to take a derivative, you want 2 points. This is 0. If it is 0, the next, you want a function to be able to take a derivative if it is 0 everywhere on the axis. Yeah, one thing you can say is that since it is 0 everywhere on the axis, the magnetic field component in the z direction, right? No, even that we cannot say because it's a curve, right? At least if it was only the change in 0 to n0, and that will be there, I guess, in the radial direction, those are 0. So you can say something about it, but not the actual answer is in the z direction. Is that clear what I'm meaning there? Right? Yes, no?
Yes, I get, yes.
The point is that, like, if simple derivatives, they talk only in one direction, right? But this is a curl. So curl is derivative with respect to x of the yth component. Right? So one has to be careful in handling that. Wherever the z part comes in, then you can talk something about it, but otherwise. So let's, since this denominator went away so easily, it seems like magnetic field should be doable right away using the magnetic field expression itself. And that is what you do in introductory physics course. This can be done for the magnetic field on the axis. So let's do that. Let's go through these steps again for the magnetic field on the axis. Okay. So magnetic field, remember, is equal to mu naught over 4 pi dq r prime. And now we have j r prime crossed with r minus r prime over r minus r prime cube. Right. Okay. Let's be on the axis. Why not on the anywhere else? Because it's harder. We'll come back to that. But on the axis again, 0, 0, z. On the axis, it becomes really straightforward. That's what we do in introductory level. But still, as a practice, because we're doing this in terms of the j prime, let's do that. Okay. Substitute j, that is mu naught I pull out over 4 pi, and let me write this explicitly. So this is 0 to infinity rho prime d rho prime minus infinity to plus infinity dz prime, and 0 to 2 pi d phi prime. And that's the delta rho prime minus a delta of z prime, and I have phi prime hat crossed with r minus r prime. Now there's a vector r minus r prime. R itself has a z component and rho components. So what is r minus r prime? But r is on the axis, right? Z minus z prime. Yeah, what's the direction of r minus r prime while it is on the axis? So it can have a, yeah, it has everything, I suppose, right? So let's write it as, if this makes sense. This is z times k hat minus let's rewrite this as r prime. Right? R prime is having a Z component and a rho component in a rho prime component. So R prime here is Z prime K hat plus vector rho prime. Is that clear? So if I were to draw this, you have 3 dimensions. So that's x, y, z prime. And you have a vector R prime now here. So that's your vector rho prime. So vector rho prime, the 2 components to that. And this is your z and z hat direction, right? So add this to that, and you get the R prime vector, in case there is any confusion on that. Okay, with that, R minus R prime in the denominator is still that simple. There's a simplification in that, correct? So that's z minus z prime, right, square plus rho prime square. This is simply because we are on the axis. And now this time this is cube, 3 by cube. Okay, do the integral. So this is mu naught I, mu naught over 4 pi I times a, and I do 0 to 2 pi d5 prime. The denominator is easy, I suppose. Or let's keep the numerator also. That's 5 prime crossed with z k hat and minus of z prime is 0 now, right? Z prime is 0, k hat minus vector rho. So vector rho prime, right? So this is a times rho hat, right? Because this was rho prime vector, but rho prime gets replaced with a, but its unit vector still stays. Divided by z minus z prime, so that z prime is 0, so that's z squared plus rho prime is a squared, so that's a squared 3 by 2. Is that clear? Questions there? Few things that went through. Any confusion or any hesitance? Ask me.
Just a little hesitance.
Yeah.
So how did we get from a power of 3 to a power of 3 halves?
Because of the square root, right? Because the magnitude has a square root in it.
Mm-hmm.
Do you see this on the board?
Yeah,
That's a square root.
Yeah, I think it just needs to sink in. I see what you mean.
Right? Or let me specify that. So, okay, the actual expression there is z minus z prime square, the denominator alone, plus rho square plus rho prime square plus 2 rho prime cosine of phi minus phi prime, right? And then square root. This is r minus r prime. This whole cube.
Right.
Right?
Right. Okay, thank you. Yep.
And then rho prime is set to, no, rho is, because I'm on the axis, this goes away. This goes away. And then rho prime is a because of the integral, right? And z prime is 0. So since I did that for A, I did this very quickly, but the numerator is new. So numerator has some tricks or has some visualization going on there. So
Okay,
that's
thank you.
B square plus A square 3 by 2. And the numerator, so this, hopefully you're convinced now. So what about the numerator? Is that anything I'm missing, well, let's say, anything I'm making a mistake? Okay, so, and there is an A there, right? Yeah, there is an A there. Because magnetic field has to have a length in the denominator. So there's an A here, and there's an A cube in the denominator. So overall, there is a length in the denominator. Okay, so that's how seemingly is okay. And there is a minus sign apparently coming out. The mu naught over 4 pi IA square. And this whole thing again is independent of the angle. Right? Again, it can all come out of the integral. Simplification just because you're on the axis, otherwise it doesn't go through. And then we have integral of 0 to 2 pi d phi prime, phi prime crossed with rho prime. Right.
What happens to phi hat cross k hat?
Oh, yeah, I didn't say that. Yeah, what happens to that? Why did I not write that? Yeah, good question. Why did I not write that? Oh, yeah, there's one more term. Yeah, but that doesn't contribute. I kind of, when I was writing this down, I was wanting to tell that, but I just kind of skipped it. Let me write that, right? So this is equal to, plus there's one more term, right? That is good point, right? So this is 0 to 2 pi d phi prime, and there is a phi prime, right? And that is crossed with, I'm putting distance there, crossed with z k hat, right? So this should also be there. Is that visible? Yeah, that's an extra term there, of course. Yeah, right. I mean, at least if you look at this. But notice, z does not depend on phi prime. K hat doesn't depend on phi prime. So this is an entity in itself, which we showed is equal to 0. So this goes to 0 multiplied by something. Right? Good point. Yeah. Yes. Okay. So this is equal to 0. Anything else that's bothering? Okay, so if we keep moving, that's equal to a minus mu naught over 4 pi I a square over z square plus a square 3 by 2, and phi primes crossed with rho prime. What is that equal to? In terms of unit vectors, velocity crossed with r hat, right? Position. Velocity crossed with position in circular motion. This sort of omega crossed with r. What is that? Is that omega crossed with that? Probably not. Omega is no, right? No, whatever. Just okay. Okay, what is this one? Let me not go into mechanics. I will make a wrong statement.
Should be minus z hat.
Good. So that's minus z hat, right? Which should be omega. So I think the point is velocity crossed with position. What is that equal to? That's omega, I suppose. Right? And r hat. So this is omega. No, omega r is v.
Negative.
Omega r is v, right? Omega crossed with
R.
v crossed with r. So this is minus omega r. Is that correct by any chance? Is that a true statement? That must be a true statement, I claim. I think typically you say omega cross r is equal to v. But this should also be true for circular motion, I guess. Check. Quiz. Anything that I get confused, I give it to you guys. Right. Criticize this, okay? I'm not very sure about this. I think this should be true for fixed uniform circular motion. That means velocity is constant and radius is constant. Then, because omega crossed r, you would say, then one of the r cancels out, I think, r squared. So probably, yeah. Criticize me on that. Okay, so that's ignoring that for a moment. This is d phi prime, and this is minus z hat. Prime if you want, but it doesn't matter whether it's prime or unprimed because it says z hat, it's coordinate independent. And then I can bring it out of the integral. Like unlike the other one, this is easy to do. I just bring it out, and that's equal to z hat. So that's the direction of the magnetic field. Now we know that the magnetic field will be in that direction alone, right? And that's mu naught over 4 pi times, that is a 2 pi, like that. So I'm going to, so this is the integral of d phi is 2 pi. And so I'm going to write that as a factor of 2, then I, and pi a square. What is pi a square? The property of the circle, area of the circle, right? And I want to write it like that. E square plus a square over 3 by 2. And of course, one thing we can immediately do is let's set z equal to 0. If I set z equal to 0, we should get back our result from last class, right? That is at the center of the circle. If I'm at the center of the circle, this is z hat times mu naught over 4 pi. And at the center of the circle, there is a square and a cube in the denominator. There's a surviving, and there's 2 pi times I over a. It is correct. I think 0, but that's 2 pi can be cancelled. Right, it's 2 times 3. Right, I'm trying to keep that mu naught over 4 pi separate. Okay, that should be familiar, but let's now ask, let me ask you guys that there's a pi a squared area, and then there is a current, and I said I want to keep it like that. What is current times area of the loop? Should be a familiar concept from introductory physics. Current times area of a current carrying wire, in this case loop. That is a property associated with that.
Magnetic moment.
Very good, very good, very good. Magnetic moment. So if you had a circular loop of wire, in fact, it doesn't even have to be a circle, right? There's an area, and in fact, it has a direction associated with it. The current loop gives you a specific direction. It can be coming out or going in. So magnetic moment of a loop of wire is equal to the current I going through the loop times the area vector. If it's a planar loop, then it is clear. Otherwise, you have to break it into as many loops, as many planes possible. So this is area A times, let me call it n hat. In this case, it is, if it is in a plane, then it is unique. If it is not, for example, sometimes you can think of a complicated loop, right? That's also a loop. Is that visible? Across the internet? Michael, is it visible?
Yes.
So this loop is not in a plane, right? So what you can do then is that you can break it into two loops, right, where the current is going one way and the other way. Is that clear? So in this is an imaginary line there, but there the current is made to go in both directions. One part is for the vertical loop and the horizontal is for the horizontal loop, but they cancel out. But then now you get two loops. So you can add up two magnetic moments if you want. Two dipole moments add up, two magnetic moments add up. So even if it is not in a plane, you can, it's a well-defined concept, correct? So that's your magnetic moment there, sitting in for that loop. So you can write, and for, if you have a circular loop, the direction will be perpendicular, so it's z hat. So in that sense, it is nice to write this as 4 pi times 2 times magnetic moment m divided by z square plus a square. Okay, so the moment you say circular wire, it has a magnetic moment associated with it, and, at least on the z-axis, so on the axis of the circular wire, it's given in terms of the magnetic moment. And when we think of a magnet, it's best imagined as a circular loop of wire. Right? Whenever you think of a north-south magnet, a bar magnet, when we're doing introductory physics, where we never talk about what is a magnetic field due to a bar magnet, right? If it's not, think of it as a circular loop of wire. So at least on the z-axis, you have the expression for the magnetic field. Somewhere outside, we'll talk about it in this next week. At least in approximation, we'll get it correctly in a simple form, and in its very gory details, we'll get it anyway. So whenever we think of a circular wire, that's the best analog of a bar magnet. It's so common, so it's good to know the magnetic field. Any comments or questions on that? So that's a magnetic field on the axis of a circular wire. Okay. So, do you want to say, Rob? Seem like you want to say.
Oh, I'm just waiting for the next step where we go off axis.
Okay, yeah, so next step, yeah, okay. Before I go to the next step, I want to say something about magnetic dipole moment, right? I said this is M, I didn't write it, right? So this is magnetic moment is good enough, but magnetic dipole moment. Oh, I changed the screen, but then I kept writing it. I just wrote magnetic dipole moment. That's all. Okay. Okay. So I want to say something about magnetic dipole moment. I remember that we spent a good amount of time, or good amount of content was related to dipole moment, electric dipole moment, or to point electric dipole moment. So we want to do similar things here. Magnetic, this is magnetic dipole moment. Of course, as I put it earlier, for a loop of wire, M is equal to I times A times N hat. And N hat is some direction which depends on the loop, right? If it's a flat loop, it's perpendicular to that. And this has a sense also, right? Sense of direction. If it is a circular loop of wire, it is using the right-hand rule. N hat has to come out of the board, and I gave it complicated geometry also, that also you can do. In your homework, you talk about if a charge is moving in a circle, right? So let's think of a charge moving in a circle. So as a single charge now, right? Not a current. This is a circular path, but it's going in a circle. This is a positive charge going with velocity v, uniform speed, let's say, along a circle of radius a or r. And one might argue that if something is going in a circle, that should have a current associated with it, right? The charge, like current is how many charges go across, like you stand at a door and how many people go through the door gives you a flux. So here, if you stand here, how many times, if it is going very fast, it will come itself again and again, right? Think of two doors, like the one person keeps running around and you will start keeping counting that same person and again going through the door. So in a sense, this can contribute current, right? And then you can ask, oh, that's equivalent to having a magnetic moment, right? An atom, if there is an electron going around, it can have a magnetic moment associated with it due to the motion of the electron itself. And one can also ask, what about the charge on the nucleus, right? Also, if it is moving, that's a part of your homework, right? If there is something, a charge, and if it is spinning, can it cause any magnetic moment associated? But that we will leave it alone. But let's just say electron going in a circle. In this case, if it is just one charge, at least the direction is clear that it should probably come in that direction. Let's see the magnitude at least. What about current times area, right? So I times A. Right? Let's try to see what this is. So that's Q. So Q, so there's only one charge here, right? So Q times some delta T. There's a time period in this case, right? Current is Q over the time period T. And that's very intuitively speaking. So that's pi a squared. Multiply that with a so let's do this somehow, right? How do you do this? So this is Q times A, and then that is 2 pi A over T. So I just moved that algebraically. That's not completely right, sorry. There's a 2 there, so I should divide by 2. So that tells me, so that's equal to half Q times A. That's yeah, so Q times A. And 2 pi a over t in circular motion is velocity, right? Distance traveled by time, so it's a velocity. So how fast the electron goes decides the current, right? If it is going faster, you will count it more number of times. So in a sense, that's let me actually change a little bit. Let me say this is r, right? Radius r, so that it's more familiar. So it's r. Okay, and its direction is, of course, if it is z direction, it is coming out of it. But I'm going to change this further. I want to rewrite this as now if I want to write the magnetic moment of a point charge in general, I'm going to generalize this from here. I'll say this is 1 by 2 q times r crossed with v. Okay, that is how I'm going to define the magnetic moment of a point charge, single point charge. And in this case, it doesn't even have to go in a circle. So even though I've motivated it from it going in a circle, so this is going to be the magnetic moment of a point charge just because it is moving. Okay, so that's a definition now. In fact, that has a very nice meaning associated with it. And this plays an important role in quantum mechanics or in fundamental physics, if you want. Let's divide out by m and multiply by m here. So this is equal to q over 2m times r crossed with m times v is momentum. And what is r crossed with p in mechanics? Cross product of this angular momentum, right? So this is equal to q over 2m times angular momentum. So the magnetic moment of a charge is decided by its angular momentum. So, and remember, angular momentum has very special properties in quantum mechanics. They don't commute with each other, right? X and like quantum mechanics is all based on this commutation relation that x comma p. They are not like numbers. They don't behave like numbers. Instead, this is I h bar times 1, right? And angular momentum is similar, right? Angular momentum L as a vector, if you want. This is imagine this to be any component of x does not commute with p, right? X comma px is 1, x comma py is 0, right? That's it. This one similarly is equal to I h bar. It turns out it is the angular momentum itself. Right? Careful, so this is having 2 of them, this is having 1 of them. So this is the best it is written in this form. L crossed with L is equal to I h bar. Very funny, right? Cross product of 2 vectors should be 0. In quantum mechanics, it's not. So, but that's just this being written in more correct terms. This is what I meant. But or if you don't like that, if you just want quantum mechanics immediately coming out, in components Li Lj is equal to IH bar epsilon ijk Lk. That's how either way you interpret it. But angular momentum is the best thing to study if you want to have quantum effects, which means that if you want to see that anything that has a magnetic moment should show you those effects very clearly. And that's why if you notice, remember your one of the first experiment, the experiment that really cleared up quantum mechanics must have been true in early 1920s was Stern-Gerlach experiment. I think this was the first experiment. Like before that, I should say, why did quantum mechanics begin? It was because of they wanted to study or explain the emission of light from atoms. Right? So atomic spectra coming out of atoms had to be explained, and Bohr's correspondence principle really explained that. But Bohr's principle was very, you can say, very empirical, and one could have argued that this just works, but it doesn't make sense. Right? So it was very suspicious. But then there was an experiment performed to check this quantization in reality, and that was Stern-Gerlach experiment. What is Stern-Gerlach experiment? This was in 1920s, I think, early 20s, so probably 1924. Around that, like quantum mechanics is 1925, 26. So that is right before that. And what is Stern-Gerlach experiment? Anyone?
Shooting silver.
Yeah,
Silver atoms through a non-homogeneous magnetic field aligned in a particular axis.
Perfect. Yeah. So the idea is that you have a beam of silver atoms. So heat up silver in a box and make a hole in it. That's a very easy experiment to perform. So and collimate it. So there's a beam of silver atoms. Right. So each silver atom has a magnetic moment, M. Right. So they chose silver atom because it has a reasonably good amount of magnetic moment in it. And magnetic moment, as far as we are concerned, it's a circular loop of wire. It's basically a direction. Right? Each atom has a direction associated with it. So, and since it's coming out from a hot oven, they're all randomly oriented. All these magnetic moments of each silver atom, which are millions of them, or 10 raised to 23 of them, they are all distributed randomly. And you put it in a magnetic field. Let us say, so that's a magnetic field. And I think it is important which one is north and south. I think they keep this to be north and that's south. But that shows that this is a not a uniform magnetic field. Those lines represent magnetic field. So Moses pointed out that it has to be a non-uniform magnetic field. A non-uniform magnetic field gives it a force. Now, as the beam goes through this magnet, two things happen. Because it is non-uniform, it actually experiences a force, which could be vertically upward or downward, depending on the initial direction of the magnetic moment. So this will try to get either in this way, drift upward or downward. So it experiences a force, right? And the expectation was that if you were, and silver atom also gives the feature that if you put it on a photographic plate, it will leave a mark, right? Earlier photography was done using silver molecules. So it leaves, so this was a photographic plate. The expectation was that this should give you a line in there or a distribution of silver atoms. This was a beam, so in a plane, so this should give a line. But what happens is that each of this magnetic moment, if you have a magnetic field in it, they are not completely aligned. They come at an angle and they start precessing about a magnetic field. So that's the second feature that happens. And that precision is important. And it either goes all the way up or it comes all the way down. But this was a classical prediction. But quantum mechanics or the actual experiment tells that they all are here. Like there are only 2 points. And the only way they could explain that is if you make this hypothesis. So, right. So, and that experiment kind of nailed down the quantum effects that no, this is true, this must be true. And then there was more impetus if you want to really explain this from a fundamental point of view. So that's going a digression actually. But the important point I wanted to point out is that magnetic moment is proportional to the angular moment by construction or by definition. If you define magnetic moment as per times area, then that's what it is. Okay, so we have a magnetic dipole moment definition now. Let's now go back and try to analyze a circular loop in a very when the radius of the loop is very small. Or actually, we'll take a few more minutes. So that was magnetic dipole moment. I want to now define point magnetic dipole moment. Magnetic dipole moment. Like we had the same thing in electrostatics also, right? What's a point electric dipole moment? How do you define that? How do you define a point electric dipole moment? So, so this is, remember dipole moment was D is equal to Q times A or vector A, right? So there's a negative charge, there's a positive charge, and there's a position vector A. Q times A is dipole moment. But what is point electric dipole moment? A very special thing there. Okay. You would put this together, right? To make this together, but then it should be zero, right?
Is there a delta function?
Yeah, so then you would say that Q tends to zero. So point electric dipole moment is Q tends to zero, right? But if we don't, if you just do that, then this will go to zero. But you say that A tends to infinity in such a way, so that's a two quantities going in such a way that QA is fixed. QA is fixed. Like it's a finite fixed number, so let's call it P. So D hat is equal to P hat. That's all. There is no other property. So dipole, point electric dipole moment has no feature as far as size goes, but it still has a direction. What is this volume or anything? There is no scale there, that's zero. But it still has a direction associated with it. And it has a scale associated with P. But that's a charge times distance that is coming up. Okay. How can you actually formulate this? This is not very hard. One would think that that's a really abstract concept. So you take a sphere, and this is a finite sphere for now. So that's R. Right. Now have a charge distribution, which is, so there is angle theta. So there is a charge Q. So charge distribution is rho is equal to Q over 4 pi R square. Right. And now put in a cosine theta prime also in it. Or cosine theta if you want prime this, since it's charge density. It is, and this is on a shell. So this is times delta of R minus A. Right, so it's on a shell. And one can show that this is actually having a dipole moment just because of this non-uniform charge distribution. That means cosine theta equal to 0, that is positive charges here. Negative, there is positive charges, and then the distribution reduces in strength, and there is no charge here. Right? Exactly at pi by 2, there is no charge. Otherwise, it's positive and negative. So one can imagine that there is a distribution there. But now, take the limit R tends to 0. Notice that if you were to calculate this, the electric field due to this, there is no R dependence. This R doesn't show up at all in the exactly like a point charge. There is no R dependence, it goes away. That means to say that I can take the limit R tends to 0. And that will be a dipole. So it's a beautiful concept that you can squeeze this in and still not have any R dependence in them. But that's all for electric dipole moment. So we can do the same thing for a magnetic dipole moment, right? So magnetic dipole moment, we said, is M is equal to I times A times N hat. Do the same idea, right? So we have point magnetic. So point magnetic dipole moment would be equal to, this time, not the distance, take the area going to 0, right? And let the current go to infinity. In such a way that the product is kept fixed. M is fixed. And that will be our model for a magnetic point magnetic dipole. Okay. So with that, so notice area going to 0, right? That means the radius, if you take the radius and make it smaller and smaller, it actually approaches that. So now we want to do actually a circular loop. Circular loop, have it go on the axis and have R anywhere, let's say, and we will have this radius A. So we will call this far field approximation. That means far field means approximation is that we are very far away from this loop of wire. Right? So we call it far field approximation. And this will actually show up again and again because we will do a radiation later on in the semester. There usually this approximation is necessary. We are reaching a regime in electrodynamics where unless you make some strong big approximations, nothing is solvable. Kind of. Okay. So, and this is a very nice, simple approximation you can make. Think of an atom, right? This is circular, and your relatively always observation is always very far away from the atom. 1 centimeter is very far away from an Armstrong. So far field approximation will be A over the magnitude of this observation point is very much less than 1. If it is, if A is 1/10 of the radius R, that's 10% accuracy. Right? We don't need this to be, so even though we say this is 0, it doesn't really have to be 0. If it is 10 times smaller, then you're 10% accuracy. If it is 100 times smaller, then 1% accuracy. If it is 1,000 times smaller, it's 0.1% accuracy. And very quickly, if you're 1,000 times larger, it's already experimentally great. Unless you're doing a precision experiment, you never need that much of accuracy. Okay. So again, let's go back and try to get this A, right? So I'll just have 2 minutes. I'll write down the expression. Let's say this time we don't want to make it on the axis. We don't want to make that approximation. So this is mu naught over 4 pi d cube r prime. So I'm just going to point out what simplifies actually. So this is j of r prime. Let me keep it as it is. Divided by, that is r minus r prime, which we said was, let's say r minus r. So this is z minus z prime square plus rho square plus rho prime square plus 2 rho prime. And then there is cosine of phi minus phi prime. And that is square root. We are saying r square is rho square plus z square. That's the connection between cylindrical and spherical coordinates. Radial cylindrical coordinate plus z square is r. So that is a z square plus rho square in there. So that's r square. So what are the quantities in here? So this is r squared plus z prime squared plus 2zz prime plus rho squared plus rho prime squared plus 2 rho prime cosine phi minus phi prime. So we can neglect or to the leading order. So ideally speaking, we should neglect everything compared to this r, right? So rho is going to be small, and in fact, we will also set z to be small if you want. So z is also small compared to our observation point. Is that necessary? Probably. We'll see if that is really necessary next time or not. So if that is r, this is so large, right? R is so large that all this goes away. So can we? How much can we neglect in this and still do it? And the idea would be that with the neglecting properly done, this will all be work. We will be able to do this integral completely, and it will give us a very simple looking or very intuitively understandable answer. But I'll stop here, and we'll do that next time. Thank you. Oh, I should have said from the beginning, that's too late now. Jordan cannot speak. He doesn't have his video and audio on because he's helping clear up the basement of his renters. So probably, I guess it is very loud out there. Actually, if he puts on the audio, so it will come to the class. So he sent an email saying that will work. But he's listening on the cell phone, so he's knowing whatever is going on. So he's doing E&M course while working. Good.
Hopefully you can hear.
Yeah, hopefully you can hear. I don't know. Yeah. But probably he'll have his full volume earphones and hear us over the machines that are making the sound. Yeah. I think so. Next time he'll clarify, I guess. Okay. Enjoy, guys.
Thank you.
Thank you.
Excuse me, doctor. Doctor?
Yes, Alia.
Yes. I have a question. The homework deadlines today, right?
That's correct.
So, can I submit it after 12:30?
Sure.
Or did you close it?
12:30 is good enough.
Can you?
12:30 is already over, right? Oh, what do you mean? I didn't understand. What?
Yeah. When I try to submit it after 12:30, it's closed and due to
Oh yeah, yeah, but it should be allowed. I think try again. It should be allowed. I allow few hours of it. Try again. Okay. Yeah. If you cannot, submit it as an email to me.
Okay. Okay. Thank you so much.
Yeah. It should be possible to submit. I have put few hours leverage there.
Okay.
Try again.
Okay.
Otherwise, email. Yeah. Bye, Moses.
Okay. Thank you. Bye.
Okay. Bye, Jordan.